Hi again, folks. All right, so we talked in the last video about converging and diverging lenses and concave and convex lenses. Um, Remember, when we're dealing with mirrors, a convex mirror is a diverging mirror. When we're also dealing with mirrors, a concave mirror is a converging mirror, although sometimes the rays do diverge if we have an object inside of the focal point with a concave mirror and we get a virtual image where the actual rays diverge. So we have to be kind of careful about that when we come to lenses. Lenses can be either converging or diverging, either type can be. So even though we may have a double convex lens, it could be converging in some situations and diverging in others. When we were talking about mirrors, the focal points were really simple to find. It's just half the radius of curvature of the mirror. Okay, with lenses, focal points a lot more complex. So I have provided a handout 6.25. Hopefully you guys have that opened up and you are looking at it, or split your screens if you're viewing them both on the laptop. But I wanted to walk us through the front page of handout 6.25 just on the lens maker's equation. Then I will have you guys finish up the back page and submit that to me. All right, so what we have here, light passes through the lens from left to right according to all of these pictures. Okay, so let's just keep that easy for right now. R1 is on the left side of the lens. So if we can imagine that we have a circle here, R1 goes from the center of curvature of that circle to this right-hand side of the circle, okay? R2 is at the center of the circle and it goes to the left-hand side of the circle. Okay, so I'm gonna go ahead and expand this real quick. Okay, hopefully you guys can see this, and I'm looking at my screen. It is a little blurry, so I'm going to move this up a little bit. Okay, so what we have here is, if we are looking at the double convex lens over here, we can see that we have a positive R1 because the radius of curvature is on the right side of the lens. That's the way I always remember these. There's a couple other ways that we can look at it, but if we can imagine drawing a couple of circles around these points, the R1 value is going to be positive. And I'll go back to that when I switch back to the document. Look at the double concave lens, and now R1 is negative because it is in contact with the left side of the lens. Okay, so just to keep things easy on this, left negative, right positive. Okay, all right, so I'm going to switch back to the actual 6.25. Okay, so R1 is on the left side of the lens. It's going to be, so R1 is always the left side. So R1 is always to the left. R2 is always to the right. The center of curvature is the left side of the lens. R is negative. So R1 in this is a negative value because it's along the left-hand side of the lens. R2 is positive in this situation. R1 is positive in this one. R2 is negative in this. Okay? So our equation for a lens to find the focal point has to do with both the n for the lens and the n value for the medium, as we talked about in the last video. So the 1 over the focal length is equal to n of the lens over n of the medium minus 1 times 1 over R1 minus 1 over R2. Okay, so let's look at a couple of calculations here. And I apologize, I tried to scan this on my phone and insert it. So it is not very dark. I'll kind of walk through it a little bit. We're going to look at all of these different lenses. So what we're doing here is we're using n of the lens is 1.5 and all of the lenses are in air. So that means that n lens is going to be 1.5, n medium is going to be 1.0. So for all of these, the left-hand side part of this equation is going to be 1.5 divided by 1 minus 1. So this side is just going to be 0.5. All right, R1 and R2 for all of these are 20 centimeters. So on this one, we've got R1 is positive, so notice I put 1 over 20, but then minus R2 is negative because it's on the left-hand side of the lens. So this is 1 over negative 20, and when I plug that in, I get a focal length of 20 centimeters. Okay? Now, this lens, and there's a couple of different ways to term this, but we've got a curved side, convex side, and a flat side. So this is sometimes termed a convexoplano lens, which is really weird to say, but that's the way they call it. This is a plano convex lens. Sorry, this would be a convexoplanar instead of plano. So that's the way they would state that one. So I won't use those terms hardly at all, but just knowing that we only have one side that's curved here. So notice the first side, the right side of the lens, there is no curvature. So I set this to 1 over infinity. So we basically just eliminate this. But this side, the left-hand side, so R2 is off the left-hand side. So this is minus 1 over negative 20. And I get a focal point of 40 centimeters, which kind of makes sense because only one side's curved. So there's only going to be a refraction on that one side of the light when it comes through instead of having a double refraction. We look at let's jump to number 3 here real quick. Notice the only thing different, I won't spend a whole lot of time here, hopefully you can understand this, but now this is 1 over 20 minus 1 over infinity because only R1 is present, and we get the same value of 40 centimeters for these two. Okay, now let's switch gears to number 4. On number 4, now the R1 value is on the left-hand side of the lens, so this is going to be negative, and R2 is on the right-hand side of the lens, so this is going to be positive. So notice in my equation, I have negative 1 over 20, and then just minus 1 over 20, because this is positive now. When I plug this in, now we get a focal length of negative 20 centimeters. Okay, so this lens would be a diverging lens as long as it's a glass lens that's placed in air. Okay, we flip-flop this around though, and we put an air lens in glass, and now I'm going to be getting a positive 20 in this, and it's actually going to be a converging lens. You would be flipping these two over, so it would be 1 divided by 1.5, and then minus 1. So that would make this value here negative. This value is negative, so I would actually get a positive focal point if I switched it around and made an air lens placed in glass. Okay, so hopefully that clarifies a little bit on these calculations. So what I want you to do on the back, you're going to have to draw some ray diagrams with just parallel rays. I showed you a couple of those in the last video, so you shouldn't have any problem drawing 4 parallel lines. Get your ruler out. I am going to be a little picky on that. Don't be sloppy. What I want you to do on the questions on the back, though, is I want you to start off with using the Lensmaker's equation and get the actual focal point calculated for each one of those. On my key, when I post it after I look at yours, you will see that I just somewhat scaled them to fit. So just kind of eyeball it after you get that, and then put your focal points on each one of them, and then just sketch from 4 parallel rays coming in and sketch what's going to happen to those 4 rays when it leaves the lens. So all 3 ray diagrams should look a little bit different because you're going to have focal points that are different on the back. Okay, there's your assignment, so I'll have it posted in Canvas.